seminar. Okay, let's get started. Good morning, everyone. Welcome to the College of Engineering seminar series. We don't have pizza today, but we hope that in the future we will be back to the normal, and then we will be able to order pizza. Today's speaker is Professor Zhang. Professor Zhang is a assistant professor in electrical engineering. She got her bachelor's degree in electrical and computer engineering from Georgia Tech, her master's in electrical engineering from Stanford, and PhD in electrical and computer engineering from Carnegie Mellon. Dr. Zhang's work is highly related to network science, complex systems, signal processing, statistical machine learning, and so on and so forth. Today, I think she's going to share with us her recent work in modeling the evolution of news events using dynamic knowledge graphs. I'm going to turn it over to Professor Zhang.
Thank you. Okay, thanks for the invitation. Okay, so this is going to be a low-key presentation. Okay, let me figure out how to use this. Okay, so first, like David said, my interest is in network science. Basically anything that's graph related, in the sense that the graph captures some sort of interaction between components or agents or things like that. So it's a very broad type of systems I'm interested in. What I'm going to present today is work in progress. So I'll show you some results, but it's not like, the best, greatest thing, because it's still work in progress. And for those people who are interested in the data set I'm talking about today, I'm perfectly happy to share. And I'm happy to collaborate if you happen to work in this area. Natural language processing is a new area for me, so I'm still learning about these sort of things as I go along in my work. And everything I'm sharing is done by my PhD student, Honggen. So any mistake, that's not a typo, it's also because of him. I'm kidding. But yeah, he knows a lot more the details. Okay, so the problem I'm interested in is we want to model the evolution of news. And when I say news, I mean exactly like the stuff that people write about and you read about in the newspaper, right? And a lot of people in research are interested in news these days because of fake news and misinformation, which is obviously a very big problem right now. So for us, our approach is, yes, the application is to be able to maybe come up with a way to detect fake news, although the definition of what is fake news is, of course, that could be that's not as well defined as you would think. But more importantly, we think if we model this, how news changes over time, maybe it will help us to be able to understand news cycles for different type of events. And also to be able to kind of quantify the news media, right? So a lot of research have been paid more towards social media. So like Twitter, Facebook, right? So if you read up a lot of like these natural language, social science, fake news sort of research, you see most of the attention has been paid to social media. And the reason, of course, is that it's much easier to spread fake news on social media, and there is a lot of them. But still, I mean, people do still read the news, right? And a lot of social media posts are posts of news articles. And the internet has also revolutionized the news media landscape, right? So I think, so that's what we're focusing on, is to, instead of focusing on social media, we're going to focus on quote unquote traditional media. Although you will see with the data we have, traditional media is a very small part of the internet. So what I'm going to talk about is mainly three parts. So first, I'm going to talk about the data collection that we did. So we web scraped news articles from the internet for different events. And this is all done by a computer. So and then we want to work with the natural English text from these articles. So you can imagine there's a lot of cleaning of the data that has to be done. And then I'm going to show, so we want to be able to mathematically model how English change, right? And that's very difficult because there's nothing to do with numbers. So instead of working directly with the English text, we're going to use something called a knowledge graph to try to quantify the information that's in the natural text. And then we're going to use this model Can someone mute their mic, please? Thank you. We're going to use this process, the stochastic process called Hawk's process, to try to model the dynamics of how the knowledge graph structure changes over time. Oops. Okay, so again, basic framework, we collect the data from the internet. So over time, we're going to collect a set of articles. We're going to extract from these articles using natural language processing algorithm phrases, which we call triplets, and then we're going to build these things called knowledge graphs. Okay, so the way we collected the data is we use these search engine services called Event Registry or News API. And what they do is you give them some keyword and they will take that keyword and then they will cross through the internet and give you HTML links of all the articles which has been tagged with that keyword. So for example, if I want to capture COVID, I give the keyword COVID and they will basically scrape through the internet and look for all the news articles that's about COVID. And the reason you will know the news article is about COVID is because associated with each news article is their own HTML page, and that HTML page has with it the keyword field, and whoever built that web page presumably filled in that field correctly and tagged, COVID as part of that keyword. So then we use this Python package called newspapers3k to take this HTML code, which is associated with this news article website. We're going to extract all the written text from that page, which is the article. And then we're also going to extract metadata from the page, such as author, keyword, publication date, the source of the article, whether the article contains images or not, and the title of the article. So because in a lot of analysis of news, people actually specifically only work with the title, because the title is a short phrase that is a good description of what is the content of the page. But instead of just a title, we take the entire text of the article as well. And we do this over basically every day over a contiguous time period. So it's not like we only extracted COVID news from today and then we do some sort of data analysis. Is that we're going to extract news of COVID from the way we captured it. We did it from January 8th last year until April 9th of last year. Right? So every day we have a set of articles.
Can I ask a question? So how do you choose the keywords?
So that is human. So Hongen and when Michael was working on this, they decided that these were the pertinent news of the time. Right. So if you look at the three data set I have, the first one is Jesse Smollett. So back in 2090, that was a pretty big story. Then it was Flight 752, which is the Ukrainian flight that was unfortunately shot down over Iran. So that was a major news. And then we started trying to capture data about COVID at the beginning of 2020 when it was rising up. Right. So yeah.
And when you search, you choose keywords and it is like any one of the keywords that exists in the document or all of the keywords or some function or a fraction of the keywords. Like how does it work?
So for example, like when Jussie Smollett's news was going around, if you just type in Jussie Smollett as a keyword or even Smollett as a keyword, it would just find all the articles about that case is tagged with that keyword.
Right. So that part is fine. But for example, something like COVID, right? If you have a bunch of keywords, like presumably some of the keywords may not appear in very relevant. I mean, there may be something on Pfizer vaccines, for example. Okay. And they may be talking about mRNA and things like that. And they may not use some of the common things that we say. They may be saying coronavirus instead of or SARS-CoV-2 instead of COVID. So how does the search happen? Like what? So is it based on all the keywords should exist in the document or only some of them? Right.
So for event registry, it would be like Google, right? So you can probably do complex things like COVID minus mRNA, like things like that. But
Right.
whether the search engine is smart enough to really finely tune your set of results to your specific inquiry, that is not guaranteed.
But
So
I'm actually asking something more simple. I think more factual. Like, so when you created the database, right? How exactly did it work? Like, did you search one by one per keywords and then sort of concatenated all of them, or did you search for like certain combinations of keywords, or so how exactly did you create the database?
oh, we just use one keyword. You can just say Jesse Smollett,
Oh, so for COVID, what was the keyword you used?
COVID.
Oh, so this is the database that includes COVID in the text.
Yes. Um,
I
right.
see.
It's so actually one reason if you look at the collection period, we stopped in April of 2020, which obviously COVID did not stop at the April of 2020, is because we were getting so many hits. There were so many articles each day, like tens of thousands of articles that we couldn't even, it was beyond our ability to even source through it. So it is true, if you use a wide keyword like COVID, it's going to give you a lot of articles, and a lot of them may be, like you said, like tangentially related. But that's, so this is the first attempt. So maybe next time we'll fine tune it a bit. But that's the nature of the beast.
Yeah.
Yeah, so if you look, the data set is enormous, right? So for COVID, we had over nearly 3 million articles collected. And this is only the beginning of 2020. So now even it's like maybe the ramp up. But yeah, these days, if you start searching for COVID, you have COVID, mutation, strain, vaccination. I mean, there's going to be so much. But you can see the size of the data set. It's, tens of thousands of articles. Every single article has the full original text, plus or minus some HTML code that maybe was extracted automatically out. And more importantly, these articles are captured over a contiguous time period, right? So every day we have how this news evolved. So obviously these are three very different events, and the story is very different. So for example, for Jesse Smollett, you perhaps remember the story. In the beginning, he was attacked, and there was, a lot of increasing interest. But what really generated the interest is like sort of like in February was when the Chicago Police Department decided, I think they charged him with something, or perhaps I don't know if he was arrested. But so you can see there's like two waves of interest, right? And this one, the left plot line just shows, because when we web scrape the article, we know exactly which news source comes from. So the left one is just a breakdown of all the major news. So you have sources from Reuters, Wall Street Journal, CNN, Fox News, and so forth. And then on the right is the number of articles from all possible, when we do the search engine, from all the links associated with each of the articles. So you can see that, when we think of news sources, these major news sources make up a very small fraction of the actual number of articles that's published on the internet each day on these news events. So whether how many people read the non-major news sources, I don't know. It might not be, perhaps it's not as lopsided as this. Like, it's not like 90% of, I don't know, maybe 90% of the population do get their news from some sort of reblog or something, instead of from the original source, like CNN or BBC. But what was surprising is how the tiny percentage of actual original articles that was written and posted on the internet from these traditional news media. Right. So this is just this is the Jesse Smollett case. The Flight 752 case, that's what I would think is a typical news cycle, is that it's a ramp up of news, and then because of the inattention, and then it very quickly, the story broke, people post, and then it would die down over time, as opposed to having these sort of peaks, periodic peaks. But again, also the same story, the traditional news website, they only make up a small fraction of the articles on the internet that talks about this event. And then with COVID, you see this basically increase from January also until April. You see this periodic pattern because of weekends. So we realized when we were started looking at the data is that you kind of maybe should throw weekends out because the number of articles posted over the weekend is less than over the weekdays. Okay, so that's the 3 news data set we have. And again, we also, each one has the original text. And so I do not believe there's any data set out there that's like this right now. But we can't work with English, right? The English does not, you can't add a, I don't know, like 2 English words together and have it make sense. So we need to have some sort of representation. So the way we choose to do it is we decided to build this thing called knowledge graph from the natural text. So what it's really doing is it's looking for this triplet, what we call the triplet pattern. So which is object, verb, object, right? So that's the most basic English sentence structure. It's usually subject, verb, object, but same thing. So so this is a triplet. You have a head, which represents the object, a relationship, which is the verb, and then a tail, which is the other object, right? So this is the base component of this knowledge graph. And the good thing about this is this is based only on lexical constraint. So the natural language processing algorithm goes through the text and it looks for verbs because there's only a finite number of verbs in the English language. And then it's going to find the verb, and that's the relationship. And then it's going to go to the left of the verb and look for a noun phrase, which is most likely going to be the object or the subject. And it's going to say that's the head of this triplet. And it's going to go to the right of this verb phrase and look for another noun phrase that's most likely to be the object, right? So it's basically, you're kind of relying on how nicely patterned this sentence is, because the machine this is not a intelligent algorithm. It's not going to be like, oh, this makes grammatical sense, or this actually makes sense when I write the sentence. It's just going to look for verb, noun phrase to the left, and noun phrase to the right? But because of there's no learning or anything involved. It can be fast, and it can do this for the tens of thousands up to millions of articles that we have. So here's a simple example, right? So again, it's the original sentence. Some journalist, some writer, spend time crafting this beautifully original sentence that says a lot, and this natural language processing algorithm, which is called Reverb, is going to take it and reduce it to a simple phrase. So Iran had denied for days. It brought down the plane. Iran brought down the plane. U.S. So you see, it's not. It's like a, I don't know, like a 5-year-old summarization of the complex ideas in a sentence. So it is imperfect, but it's natural language processing, right? You're asking a machine to extract information from a human written sentence. But from this example, you can see that there is some problems, right? Because it's just looking for nouns and verbs. So what the machine doesn't realize is that it brought down the plane. It's to a human is semantically identical to the sentence Iran brought down the plane, right? Because it here it's referring to Iran. The only reason you captured this is because it is the closest word to the verb phrase on the left, right? So after we extracted these triplets, we have to do a lot of cleaning up as well. So the first thing is to do the pronoun replacement. First, you gotta hope that your algorithm can replace the pronoun with the correct thing it's referencing, and then also then to sort through the fact that a lot of these things, even though they're written differently, they're semantically identical, right? Like a human would know these 2 sentences are exactly the same, but because they use different words, a machine will be like, oh no, these are 2 completely different things. So that takes some, that actually takes a lot of time and effort to design. So again, we use we use existing natural language processing toolbox. So there's 2 big ones, SPACI and LTK, to do these things. And also when you work with natural language processing, you want to remove things like the stop words, like so der, and but, so things that shows up all the time in English, but to a machine, this is just, if you keep those words, it's just going to, there's going to be so many occurrences of those over the other major informative words. And then again, we tend to use acronyms, US, United States of America, and all these things. As a human, we know they're the same thing. To a machine, they're all completely separate things. So you got to tell the machine that these are actually the same concept. Right.
June, like you said, you had an algorithm to replace pronouns with nouns, right? So
Mm-hmm.
what's the algorithm?
Well, I didn't build it. It's just Spasai.
But how does it do it?
Hongen, I do not know the detail.
Okay, because
Yeah.
that is potentially difficult, right? And it's not. Uh, yeah, that's potentially difficult and probably requires some amount of linguistic programming, right? Like, I mean,
Yeah. Right. So that's why we use
uh,
existing two boxes. But you might be overthinking it. It's just like the reverb. You might be overthinking it. I mean, these are not 100% guaranteed to be accurate. It could just be it knows, of course, which one's a pronoun because that's a finite list of possible words. It's just going to do a search around the words near it and then hope for something that's capitalized. It will also recognize proper nouns, right? So, but
yeah.
whether it's accurate or not, that is, unless someone wants to go through 10,000 articles, themselves, I'm not sure about the accuracy rate.
Right, but
Um,
it's important to know kind of like what it is doing, right? I mean, if it could be doing something like it replaces all subjects, all if the pronoun is like in the place of a subject, it replaces with just the subjects. But then like it could be a simple rule like that, which may or may not work, or they may be doing something more sophisticated, right? Like, so it's kind of important to know to get like a ballpark on how accurate it is.
I
Uh,
mean, each one of these cleaning up effort is its own PhD. So yes, I mean, they all, I mean, the most sophisticated would be they build some sort of they train some neural network on it. But then the least sophisticated would be a lexicon string. But the end of the day is natural language processing algorithms is an imperfect tool to look at text because these are human generated and humans understand best, and you're asking a machine to do it. So, but there are
right,
existing tools out there, right?
right. But when you said cleaning up, right? Like, what do you mean by cleaning up? Like, is it like manual intervention or other set of algorithms?
No, of course not. You use the existing function in these libraries, right? Unless you want to write your own.
Right, right. So, but then again, it's the same thing, right? Like we do not, so we may not be aware of how. I mean, the reason I'm asking is like, isn't if we have no idea about how accurate it is, maybe it's better to just leave it as pronouns. Like, so you at least have partial information rather than wrong information.
Yeah, but the only thing is, I mean, so natural language processing is not a new field. So for sure, these are better than leaving it. I'm just saying, I don't know if the accuracy rate is 100%. I'm not even sure if it's 90%. But they are sophisticated because they have had years of development, right? Anyway, but we use existing tools to do this. But anyway, the way is that, I mean, you would say, like, so what you can see is that the number of extracted and clean triplets is highly correlated with the number of articles, right? So when you have a lot of article count per day, you also are able to extract a lot of triplets. Now, whether that is, so it could be that you have a lot of articles, but you have very little semantic information. So then you will say, oh, okay, well, maybe the triplets are like, it's not like that day I have any more knowledge about the event, so the triplets shouldn't be so high. So, but there's a lot of back and forth between, is the triplet a perfect representation of natural language, right? But still, it's a representation. Otherwise, what they do usually is they do counts, like you count the number of occurrences of certain words in the article. But that's even more a coarse representation, right? Because in that case, you throw out the words completely. You just keep numbers. But it's a difficult problem to work with natural text because we're not, it's not like we take a sensor measurement and then work on that. But just the idea of what knowledge graph is. So when we extract these triplets, we're using each one of them to build a knowledge graph. We call it a knowledge graph. But in essence, if you were to do a Google search for a knowledge graph right now, that's not exactly what a knowledge graph is. So right now, knowledge graph is basically a graph representation of a database. So I think Google invented it or something. So what they use these right now is to do search, right? So if you type in on Google, like who painted the Mona Lisa, very quickly Google will give you the Wikipedia page of who painted it and everything. And the way you would do that is because it has this built-in representation, which is a database, but maybe more visually appealing is to think of it as a directed graph. And when you go path to path, right, you can answer queries very quickly. So you could very quickly see that Da Vinci painted the Mona Lisa, and the painting is in the Louvre, which is a museum, right? So by going through this path on this graph, you can generate these automatic answers very quickly. And that's how a lot of these automatic query engines currently work, right? So what we're doing is we don't have the manpower to tag, that Mona Lisa is a painting, Da Vinci is an artist, the Louvre is a museum. That does require a lot of manpower to tag and train on. But when we generate these triplets, we're going to take the relationship of the triplet as the edge, and then the head of the triplet as the starting node, and then the tail of the triplet as the ending node, right? So you can visualize how you can go from triplet to a graph which is in this shape. But because the data has not been curated into a formal database, it may be that when you do this path search through this knowledge graph, you may be able to get a sentence phrase, but not as informative to a search query as Da Vinci painted the Mona Lisa, which is located in the Louvre, right? But I just wanted to formally introduce knowledge graph, because that is one of the things that's, I don't know, hot technology right now. Anyway, so we're going to take the text, extract the triplet, use the triplet to build the knowledge graph. So there are pros and cons to this approach, right? So the pro is we still retain some semantic information, right? The whole idea is I want to be able to mathematically model how these news articles, the information in these news texts change over time. But they're English, and there's no way I can do that. So I need some sort of representation. And to me, purely numerical representation, like the frequency count of specific words, isn't very informative. So I'm going to use this knowledge graph idea, right? So the knowledge graph are simple. The triplets are very simple phrases extracted from the text. And there may be, when you do these pronoun replacement, the cleaning up, you may make a mistake. So it's an imperfect representation, but at least the triplets and then the subsequent knowledge graph, it still retains some semantic information from the original text, right? The con is, so I'm still interested in a mathematical model, and there's a reason why you don't really hear about a lot of dynamic process models involving graphs. One is it's still a research area under development, and two, it's very complicated to model how graphs change over time, right? Because now you got edges and nodes, and then things can change. And in addition, here there's words associated with both the nodes and the edges. And then there's directions to the node. You can imagine that there could be two words, a head and a tail, that has different type of verbs associated with them. So it's complicated to try to even build a math models around these knowledge graphs, right? So that's the con, is that it's not as simple as just looking at a vector of frequencies of word occurrence. This is a much more complicated structure. But then the pro is that it retains some semantic information. Okay, so just to give you an idea of what knowledge graph looks like. So I have news articles over time, right? So on day one, I'm going to take all the articles and I'm going to build this knowledge graph. And then on day two, I'm going to have new triplets that I can extract from the articles. And then I'm going to add the new triplets to the graph on day one. On day 3, I'm going to take all the articles, extract all the triplets, and then add those triplets to the articles to the knowledge graph from the previous day, right? So you can see, imagine over time, this thing will grow very, very quickly. So unfortunately, you cannot see the words. So here we didn't even bother plotting the words associated with the edge, because that would just make this into it would be very complicated. But you can see that some nodes, this is regarding the Jussie Smollett news. Smollett, for example, is a phrase that was extracted, and that word is part of a lot of triplets, right? And you can see that over time, it grows until, again, for visualization purpose, it's very difficult to visualize. But we want to do analysis, right? This is how we decided to go from text to this sort of representation, and we want to do analysis. And my interest is in network science and graph-based analysis. So what I'm interested in is how to analyze this particular structure. So the only thing is there are words associated with the nodes and the edges, but they're kind of hard to deal with. So for now, I'm just going to only look at the structure of the knowledge graph. So I'm going to sort of, in some sense, disregard what the actual words associated with the nodes and verbs and the edges are. I'm just going to look at how things are structured together. It would be nice, of course, to be able to explicitly consider the words, but that's future work, right? So the most basic thing I could do is just to look at the structure of this graph, and that's this area called network science type of thing. So first is the thing I could do is I could look at the number of cycles in this graph, right? So if you can imagine, this is a very, very simple visualization of how my knowledge graph can look like. I have nodes and I have edges. So the nodes are the head word and the tail phrase, and then the edge is the relationship or the verb phrase, right? And what I'm going to look for is the number of cycles. So a cycle is this sort of triangle, or any sort of loop is considered a cycle. So we know from previous work on graph structures is that a graph with lots of cycles are densely connected, right? Because everyone is connected to everyone else. And so we can do that. We can do that analysis so here on day 1, I extract the triplets, I build a knowledge graph. On day 2, I extract the triplets, I build a knowledge graph. On day 3, I extract all the triplets, I build a knowledge graph. So each one of those knowledge graphs, I could look at the number of cycles. So what you generally see is that the number of cycles for the knowledge graph, for this particular data set, the Jussie Smollett data set, it's actually fairly small. There's actually not so many number of cycles, right? I mean, considering how big the graph can be, this is fairly small. Then the other thing we want to look at is the diameter. So the diameter is the longest, shortest path distance between two nodes. So for example, it cannot be just the longest, right? Because the reason is because the longest, I could just keep going in a cycle, and then you could have infinite path length. So that's why it's the longest, shortest path length. It's a little awkward to say. But in this very small graph, you can easily see that the diameter is the longest, shortest path length is to go from node A to node G, right? So I could go A, B, D, E, F, G. Oops. Oops. Okay, yeah. So the diameter is the number of paths, and so the number of paths is 5. So then we did that to look at the knowledge graph. And you see that it's relatively small diameter, right? So again, of course, the diameter will change day by day because the set of articles we collect each day is different. But it's about roughly 14, maybe 12. So that's like, 13 nodes. So again, given the size of the graph, right? Again, each day is hundreds of thousands of articles. That doesn't seem very long, right? So it's relatively short. So these graphs are relatively closely connected. And then the last thing you can check is average path length. So you look at all the possible paths between any two nodes in the network, and you take the average. So again, when it comes to the knowledge graph structure, it's about 3 or 4, right? So it changes, of course, from day to day, but on average, the average path length is about 3 or 4. So that means it's about 3 or 4 triplets. So if I were to go from one starting with one triplet, most likely I will encounter, it will be a path of 3 or 4 triplets before it ends, right? So it's not a very complicated idea. If you think of each triplet as a short phrase, it's like 3 or 4 sentences stuck together, right? So these are just because again, because of the graph, the size of the graph and the thing associated with the words, if you can't just do a direct visualization, right? You go find a very large screen, you visualize the graph, and then you try to deduce patterns from that. That's not a very, usually it's not a very, it's a way to do it, but it may not be very informative because one, your graph is too big to visualize even on a very large screen. And two, depending on which algorithm you use to draw your graph can either look like a complete hairball, like basically a bundled mess, or it may, make you think that there's some structure there, even though it doesn't really exist just because of the way it's drawn. So visualizing the graph is, of course, we like it because it's pretty, like I showed on the title slides, and it can give you some intuition, but it's not 100%. You cannot rely on visualizing the graph to look at the structure. So you have to rely on these sort of statistics like diameter and average path length to try to get a sense. But from these basic analysis, at least of the Jessie Smollett data set, we kind of have an idea that this knowledge graph each day built from the articles collected that day, it has a very low number of cycles and it has a fairly low average path length. So what it means is that it's mainly like these sort of, it's like a star hub sort of structure. So you tend to have these nodes which are like the hub, and from each of these nodes, there's many connections. So it's like a star. And it's not like hub. It's like these hubs are somewhat interconnected. So the diameter is not that long, right? So it's kind of like you have a rough idea from these statistics of what the structure of your knowledge graph look like. And it's true, we know that the hub nodes refers to these words that occurs very frequently in the text, right? So for example, Smollett in the news data set regarding Jessie Smollett is a hub node, right? So this is the central node, and then everything else is sort of like spun around it. You can see that police is also a hub node. That is a word that gets mentioned very often, right? And Chicago and so forth. Okay. So that's one thing is you can do is you can look at the structure of the knowledge graph each day. But I'm also, again, interested in how news changes over time. We have this dynamical system. So what we want to do is we want to understand how this knowledge graph, this cumulative knowledge graph grows, right? So instead of looking at knowledge graph each day independently of one another, we're going to have this growing process, right? So we're going to have the knowledge graph on day 1, together with the knowledge graph on day 2 is going to be G12. The knowledge graph on day 3 is going to be the knowledge graph of day 1 with the knowledge graph on days 2 with the knowledge graph on day 3, right? So I'm going to write that as G13, and then all the way I can arbitrarily say G1n, right, up to day n. And so it's this this growing knowledge graph, this cumulative knowledge graph process that I want to model mathematically. Oh, so that's the animation just to show you how this thing is growing over time, right? Yeah, so it's a visualization. And this is all extracted automatically from a bunch of English text, right? And it, yeah, so zoomed out to see. Okay, yeah, so again, it's a graph, it's changing in time. How could I possibly try to model this mathematically, right? What I'm going to do, I'm going to have a vector or matrix representation of a graph, and then it's going to change over time. It's very complicated. There's no one default model to use to model the changing structure of a graph. So instead of going directly to the graph, we're going to instead consider features from the knowledge graph. So I'm not going to explicitly model how this graph structure is changing over time because that's very complicated. Instead, I'm going to consider what we call 4 different features of how the graph can grow. And those 4 different features, you can think of them as the state of your system, right? So we go from this very complicated graphing to maybe just keeping track of 4 things. So it's much simpler to model, right? And the thing we said is, how could I possibly think of how this graph structure can grow over time? So we call them copy, mutate, append, and extend. Okay, so consider you have a knowledge graph, right? A knowledge graph already built from all the articles in the past, right? So it's going to have some triplet in that particular knowledge graph. So what you want to do is you want to understand how that triplet is going to grow over time, right? Because presumably there might be more triplets attached to it or something. So, but there's 4 ways that that triplet can change, right? So one is copy, in that I already have this existing triplet. The articles that I capture on the next day is going to have a triplet which is identical to an existing triplet. So basically the knowledge graph from day 1 to day n remains exactly the same as the knowledge graph from day 1 to day n-1, right? So the only thing it did was it just copied the same triplet, the same sentence appear, right? The other way it could change is what we call mutate. So the knowledge graph, a new triplet appears on day n. It's going to have the same head and tail node, meaning the subject and object is the same, but then the verb relationship is going to be different, right? So then now my cumulative knowledge graph is the original knowledge graph plus this new edge between 2 existing nodes, right? And then the other way is append, which is that the new set of articles introduce a new triplet where either the head or tail comes from the original triplet, right? So this is how you could think that this triplet can grow over time, is that it just either it's appending to the tail or it's appending to the head of an existing triplet. And then another one is extend, which is that in the original set of triplets, they're disconnected, meaning that there's no verb phrase joining these noun phrases. But then in the new article, there's a triplet for which there's a verb which joins 2 original noun phrases, right? So these are different ways of how you think, or how we thought that the knowledge graph could possibly change structure over time, right? And the thing is, this process, this is happening to every single triplet that exists in the past graph structure, right? So there's a lot of these events could happen, and this event could happen for multiple multiple events. So append, extend, they can happen to the same triplet, right? So they're not exclusive of one another. Anyway, so we thought this is a way we wanted to model how this knowledge graph could change. And then we were saying, well, okay, what we really wanted to do is, suppose we can build this dynamic process. What do we want to use this dynamic process to look at, right? So again, in lieu of fake news, because I don't know, there may be fake news in these data sets, but I wouldn't know where they are, and I don't want to read through 10,000 articles to find them. So in lieu of fake news, what we said is, okay, maybe we should consider again, how the major news are, how articles from these quote unquote major news may differ from the articles from these quote unquote gossip blogs, right? So this is the assumption that these gossip blogs are not just copy and pasting news articles from BBC or CNN. They're actually rewriting it, or they're taking bits of it. But we consider, the major news sites, Reuters, CNN, and then I think this is from an internet list of what is considered to be gossip blogs. So TMZ, I have never heard of some of these, Socialite Life and whatever, right? So, but there's some of these. So we're going to look at the knowledge graph we can build from only news articles collected from these sources and news articles collected from these gossip blog sources. Yeah. So again, even just from, so what we want to see is we want to compare the number of these type of events, right? So the blue curve are from the major news, and then the orange curve is from the gossip news. So this is the average number of copies for the Jussie Smollett data set per day, right? So if it's high, it means that the knowledge graph grew with a lot of copies, meaning that the same triplet appeared the next day as the day before, right? So imagine if I just pasted the same article on day 1, on day 2, that would be nothing but copy events, right? So a high copy, it could be that what this means is that when you give a news article, some of the paragraphs are like recaps from the previous day, right, of what has already happened. So that could explain why there's a high number of copy in the big news, because they tend to be, the articles may be longer, and then a lot of those paragraphs may be recaps from what happened, what has happened in the story originally. But the surprising thing is, so the gossip news doesn't have much copy events. Then there's mutate. So the big news and the major the gossip blogs behave similarly. Then append, also somewhat similar, and extend, also somewhat similar. Okay. So just last thing, just to throw in mathematical models. So what we discussed so far is just data analysis, right? I have the data set, I do the transformation, and I have some idea of these are the things maybe I should look at, and I go through the data and I have some sort of summarization to try to get a sense of what the data is. And that's one of the most important things when you work with data sets, especially very large data sets, is it really takes you time to familiarize yourself with the information that's even in the data. So even now, there's stuff that in there that we can look at. But I'm still interested in mathematical models. So just for the sake of completeness, to talk about very quickly, very few equations, is the mathematical model that we want to build in order to look at these sort of dynamic. So this thing is called a Hawkes process, which you probably will not hear. Usually it's more relegated to research. So it's a continuous time counting process, meaning what it does is it models when things occur, right? So the occurrence of things. So people have been using Hawkes process to model earthquakes, right? So I know that earthquake occurred this year, earthquake occurs next year, and so forth, right? And people use it to model Twitter post dynamics and financial transactions. So a more frequent model that you will use more often than Hawkes process is the Poisson process, which is easier to learn, to use, to understand. But the reason that a lot of these things, like for Twitter dynamics and so forth, use the Hawkes process is because the Hawkes process has history. So it's what is called a self-excitatory process, meaning that if I have a lot of Twitter posts within a very short time period, it's highly likely that I will have another Twitter post very in the near future. And this, of course, you can see why it applies to earthquake is that what they've shown is if there's a lot of very frequent minor earthquakes in a region, it's very likely that there will be another earthquake in that region, right? So this sort of behavior is called self-excitatory, and this sort of behavior cannot be modeled using a Poisson process. So you use a more complicated model, mathematical model, which is called the Hawkes process. Anyway, so not running out of time, so not going to go to the details, but the entire thing about Hawkes process is the dynamics is characterized by this conditional intensity function. Whereas in the Poisson process, the dynamics is characterized by the rate, which is lambda as a constant. Here, this lambda is a function, it's a stochastic function of time, right? So you can see why it becomes more complicated. But again, it has this desired behavior of self-excitatory. But in order for us to use the Hawkes process, we had to make some modifications. So one is our data is discrete time. We really only know that the article is posted that particular day. Sometimes they're a little bit nice and there's information on the exact publication time, but usually it's the midnight of the publication date. So we really have a discrete time observation. So we have to use a discrete time process. And also we actually have, we want to keep track of the dynamics of 4 events. So copy, mutate, append, and extend. So we're using a multivariate Hawkes process. Right? And then also, because this is real world data, it's a non-stationary process. So I'm not going to say that given my observation on day 1, I'm going to be able to predict or model what is going to happen on day 25. That there's a lot of non-stationary dynamics that could happen in such a large time frame. So I'm going to say, okay, give me the observation on day 1, maybe I can predict what's happening on day 2 or day 3, right? So we're using short time windows to get by the non-stationarity. Okay, so again, given the observation of when these sort of event happens in the past knowledge graph, we're going to learn the parameters to predict the number of events of copy, mutate, append that happens in the future. And this is just a way to see if we can fit a Hawk's process model to our data, right? So we can look at the data, but we also want to build the model because the model also tells us, gives us some additional insight of how this thing is growing. And then the way we check is we have the true number of events, and we just compare it with the predicted number of events, and because it could be negative, we square the value. So for some things, so for copy and mutate, the prediction is okay. I mean, you have very low error, but to be honest, copy and mutate is also, it's not that many things happen, right? So if you just guess 1 or 2, you might just have a low error by default. And then for append and extend, usually we have very low error, except there's a very sharp peak in error around the time when when Jesse Smollett was charged by the police department. So that we're not sure yet. So again, work to continue. Yeah, so that's the basically gist of the talk. Is there's a lot of things, but the basic idea is you have natural text and you want to work with the text, so you have to transform it in some way. So we decided to do it over as a graph structure called a knowledge graph, which really is built from these short triplets automatically extracted from the text. And we're trying to learn the dynamics of how this knowledge graph changes over time, and we use Hawk's process. Okay, so thanks. That was long.
Thank you, Professor Zhang. Any questions from the audience?
Well, I just have a question. I'm just wondering, how do you, what is the plan to distinguish between the fake news? I meant, what kind of algorithm do you want to use? Is it using the feature, those features to understand that? Sorry for, yeah.
So I'm hoping first, the most important part, I have to get my hand on a set of fake news data set. But the idea is that presumably the assumption is fake news may have a different, so we have this dynamic, right? So however you want to say, whether you can remember what these mutate, extend, these events are, somehow it's some sort of dynamic of how news changes. So if fake news have a different dynamic, then, or it's it's not just one single fake news, right? It's the injection of fake news events over time. If it has a different type of dynamic, then you can build a classifier to say, hey, I don't think this type of event should have this sort of dynamic, something weird is going on. Maybe you want to take a look at this particular source or this particular set of sources.
Yeah, thank you. Actually, I just asking because it's not clear for me how to distinguish between the actually fake news or something we call it novelty, something new, which actually doesn't follow the previous pattern.
Yeah, so that's what I'm saying. Like the definition of what is fake news is very difficult to quantify, right? There's fake news, misinformation. So all I know is a lot of existing research on fake news right now uses social media, so Twitter. And what they see is the tweet pattern of fake news is different from the tweet pattern of normal tweets, whatever that means. But you can also look at it from a semantic perspective, like maybe the language people use to write fake news is different from the language people use to write real news. Although that's why we looked at the gossip blog versus the big news, right? We're thinking, okay, maybe when people write things for TMZ, or like these sort of celebrity gossip blogs, maybe they use a different words from Reuters or from CNN. But at least for the Jesse Smollett set, it's not that different. It could be that, again, we need to do a little bit more of a finer analysis of which one of these is truly gossip blogs, because maybe, I don't know, people they hire writers the same as CNN will hire writers. So that could be targeted, but it's certainly with the exception of copy, there doesn't seem to be a difference, right? So, but the hope is that whatever, well, not hope, but the idea is that the dynamics of how someone present the information may be different depending on if it's fake versus traditional versus novel, that kind of thing.
So,
Thank you.
so Mohammed, if I can add one more thing, right? It's like June was saying, like it's really your definition of what is fake news. For example, I don't know if you remember, but during the COVID crisis, Trump was saying something about injecting bleach. Okay. Now the question is, do you consider this fake news or not? Right? Because in a very real sense, like the way the reporting about injecting bleach would have gone through would be kind of identical to what Fauci said, because it all comes from the same news conference. It's just the a different piece of information. We know it is ridiculous because of the context, right? Like we have a knowledge base of what is real in the world, what is possible, what is not possible. But for others, like their context is different about what is possible and what is not possible. They may actually be inclined to think something like what Fauci is saying is fake, but what Trump said about injecting bleach makes more sense, right? So when you say fake news, right, and it's really the context of what is the information that also matters. So that's where a lot of things become tricky, right? And like June said, the primary way we try to detect fake news, or like we have been successful in detecting fake news, is to see the pattern in which it spreads, right? Rather than the semantics of the content, right? So it's just like but it's something like if you have a good way to do it, I think it's very useful. But I think as of now, I think it's a problem that is very much open, I think.
Thank you.
I don't know if there's undergrads here or if anybody knows undergrads who are looking for X96 projects. I have like a 3 million COVID articles. If people want to work on this, I'd be happy to take Humanize. There's probably Trump suggesting bleach. I know there's some fake news embedded here. I just don't have time to go through 3 million articles.
Yeah.
So I have a question. I guess we try to detect, identify fake news here. I guess the assumption is that the information is kind of not controlled, right? I guess my question is, if in a scenario where there's a strong control of information or whatever, like control and manipulated, for example, let's say government manipulating whatever news, would this still applicable to those cases?
Yeah, so I mean, this more than just dynamic, it's also makeup, right? So this is why the internet's uncontrolled, because CNN makes up for like less than 5% of the actual article content. So I imagine if it's government control, you're going to have government control news source making up like 90% of the articles out there. So just this was the most shocking thing to me, was just like, again, I don't know how many people are reading these blogs, so it could be that this is not the readership, but the fact that, I mean, we've relegated traditional news media to such a small part of the internet. It's kind of mind-boggling. Maybe people are getting it from Reddit or something, but still.
So David, like, did you watch Chernobyl, the TV series? There's a
Not
series
really.
on. Okay, so the very first line in that, one of the first lines in that series is this: when there is so much lies. I mean, he's speaking of Soviet Union, but it's probably true of social
Yeah,
media today.
yeah,
When you see so many lies, the problem is not that people will believe the lies. The problem is that people will not recognize truth when they see it.
yeah.
And that's actually very much true. Like, and that is exactly like what you're saying, right? Like, I mean, you can say something is fake news versus something is real news if there is a basis for reality. Once that basis for reality goes, because there's so much fake news, you cannot. You can only, because statistics can detect novelty. It can't.
Mm, yeah,
So,
yeah.
yeah.
The other thing, I mean, I'm not, again, I mean, to me, it's the dynamics that's interesting, right? Because you can see that it's kind of like breaking news, everybody reports on it. And then actually, I think it's kind of nice that the tail is kind of slow. I was expecting that everybody reports on something, and then immediately on day 10, they're like, oh, whatever, stop reporting. But at least for these major events, it's a gradual die off. So I'm not sure, for little events, maybe it's a very sharp die off. So there's actually, if I get funding, I would like to collect more data because this is only really 3 events. So we want to also automate have a better idea of what kind of data to collect, because I think different type of events will have different types of this die-off profile, so to speak.
So how about they hire people just to flood all these blogs or whatever, and then you sort of kind of control spreading the fake news and all that, or maybe internet bots or something, just I don't know if this whole thing would be if it's even possible to manipulate it to a level that it's gonna change the results. But I'm just curious, how much interference, I guess, a government can have in these
So
kind of.
David, just to say something, I think something like 60% of Republicans believe that Obama is not born in the US. It doesn't have to come from the government. Like news can be manipulated very easily, right? Like so it's an example, right? Like, and you can take, it's not just one side. You can take both sides, and there'll be some ridiculous things all of us believe, right? So I guess it, to some extent, it's always happening. It's just that we are more aware of it right now, right?
But this is not before the internet. There's no way you would. Reuters makes up 10. I mean,
Oh,
CNN makes up like 10%.
before the internet, you have that the British royal family, like they had like bunch of massacres all over the world, and including like this is in 60s and 70s, and no one ever heard about them, right? So it's like there are all these stories. I think it's just more, I think it's more accelerated right now. It's more sharply in focus, but some amount of manipulating what is truth has always happened in society, right?
Sorry, someone asked, what about
Yeah.
handling conflicting stories from different sources? Is there a weight associated with the sources when forming the knowledge graph? So currently, no. And also currently is not smart enough to realize when they're conflicting stories. Because it's when Reverb extracts the triplets, it's a pure lexicon relationship. It doesn't know if I say A is B and then somebody else say B is C. It doesn't have an intelligence built in to say that those are different. You know what I mean? Like that was a bad example. But maybe in the future. So I think that's actually what when people really build true knowledge graph, like from a knowledge database, that's when you can handle conflicting stories, right? When you actually have a database organized, but we're not there yet. But that's a good idea.
All right, we're a little over time, but any other questions before we end? Well, if no other questions, we're going to end over here. Let's thank Professor Zhang again for this very interesting talk. Thank you, June.
Awesome.
Okay, bye everyone.
Take care.
Thank you. Thanks, June.
Thank you so much.